Today we're going to introduce the idea of regular expressions. This is a simple algebraic notation that describes exactly the regular languages. In practice, it's very common to have a regular expression-like notation to describe patterns, such as patterns in text, and to have behind the scenes a compiler from regular expressions into finite automata, in particular deterministic finite automata, because these are the things that actually can be executed. So after introducing the notion of a regular expression, we're going to show you that you can convert any regular expression into an automaton, and also any automaton into a regular expression. That's the proof that the languages accepted by regular expressions and the various kinds of finite automata that we've met are exactly the same. The algebra you are most familiar with is probably arithmetic, using operators plus and times and operating on numbers. The regular expression algebra operates on languages, and it has three specialized operators. Regular expressions, like algebraic expressions, are built up by applying these operators to operand. So, regular expressions then describe languages by an algebra, and they, as I said, describe exactly the regular languages. We'll use L of E as the notation for the language described by the regular expression E, and we will describe regular expressions and their languages recursively. Regular expressions use three operations: the union, concatenation, and the Kleene star. Okay. The union of languages is the usual thing, since languages are sets. And here's a very simple example. Here are two sets, their languages, each with with three strings and with two strings. 0, 1 happens to be in both, so it will be once in the union. 1, 1, 1 is there, 1, 0 is there, and 0, 0 is there. So that's the common notion of the union on sets or languages. Okay. Concatenation is also a fairly simple operation. We'll denote the concatenation of two languages, say L and M, by juxtaposition, that is, L, M with no punctuation in between them. The language LM contains every string that is W concatenated with X, such that W is in L and X is in M. So here's an example. We are, in effect, multiplying the two languages. That is, we'll take 0, 1 from the first language, and we can concatenate it with 0, 0. That gives us 0, 1, 0, 0. We could also take 0, 1 again, concatenate it with 0, 1, and that gives us that. Then 1, 1, 1 concatenated with the two strings here gives us these two strings in the result. And 1, 0 concatenated with 0, 0 and 0, 1 gives us the final two strings in the result. Okay. Kleene star is probably something that you're least familiar with. If L is a language, then L star, which is called the Kleene star or just the star operator, is the set of strings that you can form by concatenating 0 or more strings from L in any order. That is, you can take one string from L, you take no strings from L, that would give you the empty string. You take one string from L. You take two strings from L, there can be any two strings, they don't have to be the same. You can concatenate them. You can take three strings from L, concatenate them, and so on. Incidentally, Stephen Kleene was the fellow who invented regular expressions and showed that they describe the same languages that finite automata describe. Okay. If L is a language, then L star, the Kleene star, or just star operator, is the set of strings formed by concatenating 0 or more strings from L in any order. Thus, L star would consist of the set containing the empty string. The empty string is always in the star of any language. because that represents no choices of string from L. Then with union with L itself. And then we can take two strings from L, so we take L concatenated with L. We can take three strings, and so on. Any verbs from L. Anything you can form by concatenating any number of strings from L will be in the language L star. So here's an example. Language L just has two strings, 0 and 1, 0. The star of that language, well, we can take no choices, that would give us the empty string. We could take one or the other string, that'll give us these two. We can take two choices from the language L. So if both choices are 0, we get 0, 0. If we take 0 for the first choice and 1, 0 for the second, we get this 0, 1, 0. Or we can take 1, 0 for the first choice and 0 for the second choice. That will give us 1, 0, 0. Or we can make both choices be 1, 0, and that gives us the string 1, 0, 1, 0. There are three parts to the basis in the regular expression definition. The first part is for single symbols. Okay. If A is a symbol, then A also denotes a regular expression. The language that this regular expression denotes is the language with one string. That string has length 1, and the one position of that string has A in it. Okay. By the way, in order to distinguish A as a symbol or string from A as a regular expression, we usually make the regular expression boldface, but a context should help you to distinguish strings, symbols, and regular expressions anyway. Okay. The second part of the basis is the symbol epsilon. Okay. This is a regular expression, and its language is the language that has one string. That string is the empty string. And the third part of the basis is the empty set symbol. This is a regular expression, and its language is the empty language. Okay. The inductive part of the definition also happens to have three parts. Okay. For the first part, we can connect any two regular expressions by a plus sign, and this plus sign represents set union. That is, the language of E1 plus E2 is the union of the languages that E1 and E2 denote. The second part involves the concatenation operator. We can write one regular expression next to another to denote the concatenation of their languages. That is, E1 followed by E2 denotes the concatenation of the languages that E1 and E2 denote. As we shall discuss in a minute, we sometimes need parentheses to group expressions properly. So in some circumstances, we need to put parentheses around E1 and or E2. So we might, for example, see something like that. Okay. The third part is the star operator. If we follow a regular expression E by a star, then the language we denote is the Kleene closure of the language that E denotes. Again, it is in some circumstances necessary to put parentheses around the E to make sure the operators inside the expression E group properly, like that. As with other algebras, we can and must use parentheses to force the intended order for operations. For regular expressions, the order is star, then concatenation, then plus. You can think of plus, the lowest precedence operator, as analogous to addition in arithmetic. Concatenation is analogous to multiplication, and star as analogous to exponentiation, although in the case of star, there is no power to which its argument is raised. In a sense, star means raised to all powers. Okay. For example, the regular expression 0, 1 represents the concatenation of the language consisting of one string, which is 0, and the language consisting of one string 1. The result is the language containing the one string 0, 1. In general, any string of symbols as a regular expression represents the language that contains only that one string. The language of expression 0, 1 plus 0, that's this, is the union of the language containing only the strings 0, 1 and the language containing only the string 0. The language of 0 concatenated with 1 plus 0, that's this expression, is the two strings 0, 1 and 0, 0. Notice that we need parentheses to force the plus to group first. Without them, since concatenation takes precedence over plus, we get the interpretation of the second example, that is, this one, and obviously you would get somewhat different languages. The language of 0 star is the star of the language containing only the string 0. This is all strings of zeros, including the empty string. Here's a little more complicated example. It denotes the language that we've been playing with when we talked about automata, that is, all strings of zeros and ones without two consecutive ones. To see why this works, in every such string, that is any string in the language, each one is either followed immediately by a 0 or it comes at the end of the string. Now, this part of the expression, 0 plus 1, 0 star, denotes all strings in which every one is followed by a 0. Okay. These strings are surely in the language that we want, but we also want those strings that are followed by a final 1. Thus, we concatenate the language of 0 plus 1, 0 star with the union of two languages. One is epsilon, and concatenating with epsilon just gives us the same strings, that is those that don't have a final 1. And we can also concatenate with the language containing the string 1. That gives us any string in which every 1 is followed by a 0, and then it also has a final 1. Okay. We're going to show that regular expressions define exactly the regular languages. We already have three equivalent representations for the regular languages: DFAs, NFAs, and epsilon NFAs. We need to show that for every regular expression there is some automaton that defines the same language, and for this job we may as well pick the most powerful of the three varieties of automaton, the epsilon NFA. For the other direction, we need to show that every regular language is defined by some regular expression. Here we may as well start with the most restrictive variety of automaton, the DFA. We'll begin with the process of how you convert a regular expression to an epsilon NFA. The proof is an induction on the number of operators, the operators of course being the plus, concatenation, and the star that appear in the regular expression. And we're always going to construct an automaton that has a special form, which I'll show you on the next slide. The special form of epsilon NFA we construct is suggested by this sketch. There can be any number of states in the middle, but only one start state, as is true for any automaton, and only one final state, which is a restriction. More importantly, as we build larger automata from smaller ones, we never allow an arc into the middle or into the final state. The only outside arcs must come into the start state. That is, we might add arcs like that, but you can't add an arc that goes to a state that's inside. Okay. Likewise, you can't add an arc that goes to the final state. Similarly, we never have an arc from any of these states except the final state to someplace on the outside. So you can't install some arc leaving like that. And notice that we put quotes around the term final in final state, because although this state is final if this is the entire automaton that we construct, if it's a piece of a larger automaton, then the final state will no longer be final in the larger automaton. Okay. The induction is on the number of operators in the regular expression. And here are the basis cases, the expressions with 0 operators. Okay. A regular expression without operators has to be one of the basis cases from the definition of regular expressions. If the expression is a symbol A, then the epsilon NFA we need consists of only a start and a final state with an arc labeled A from start to final. Obviously, this automaton accepts the language of the regular expression A, that being only the one string A. If the expression is epsilon, then it is sort of the same, except the arc is labeled epsilon. And if the expression is the empty set symbol, then we just have the start and the final state and no way to get from one to the other. Okay. Now we begin the induction. There are three cases depending on whether the outermost operator is union, concatenation, or star. Here's the construction for union. Suppose our expression is E1 plus E2. Both E1 and E2 have fewer operators than the entire expression, so the inductive hypothesis applies to these sub-expressions. We may thus assume that there is an epsilon NFA of the desired form for E1, and likewise for E2. We form the epsilon NFA for E1 plus E2 by introducing a new start state and a new final state. The old final states are no longer final. There are epsilon transitions from the new start state to each of the two old start states, and there are epsilon transitions from the old states to the new final state. If there's a path from the new start state to the new final state, it must consist of epsilon transitions at the beginning and end with a path that is either wholly within E1 or wholly within E2. So, for example, the path might look like this. Go here, and then wiggle around, could go through the same state many times, finally comes to the old final state of E1, and then out to the new final state. Notice the fact that there's no way to get into the green thing labeled for E1 and no way to get out of it except, as I've shown, guarantees that the path must, from the path from here to here, must either go through E1 or through E2. There are no other options. Okay. Here's the construction for concatenation of E1 and E2. Again, we assume by the inductive hypothesis that there's an epsilon NFA of the right form for E1 and ditto for E2. We add an epsilon arc from the final state of the automaton for E1, and that state, of course, then is no longer final, to the start state of the automaton for E2. The start state of the bigger automaton is the start state of the automaton for E1, and the final state is the final state of the automaton for E2. The new automaton is the concatenation of the languages of E1 and E2. Any path from the start to final state must first pass through E1. That is, it will do something like this. Then it will take this epsilon arc, and then it will do something E2. There's no other option because you can't get into or out of the green areas except as shown. Finally, here's the construction for star. Okay. Suppose we have an automaton for some expression E and we want to construct the automaton for E star. We add new start and final states, and the old final state is no longer final. There's an epsilon arc from the new start state to the new final state, so epsilon is always in the language of this new automaton. There are three other epsilon arcs as shown. The first of these epsilon arcs brings us to the start state for the automaton for E. We must traverse the automaton for E, following a path whose label is any string in the language of E. Now, when we reach the old final state of this automaton, we have a choice. Okay? If we follow the epsilon arc to the new final state, then we're done. We've found a path that has a label that is one string from the language of E. Or we have another option. We can go from the old final state back to the old start state, maybe take another path to there. Now we have a path that has a label that is the concatenation of two strings from the language of E. And we can go back again, take another path, make a label of that path would have now a concatenation of three strings from E, and so on. We can do this as many times as we like, but then finally we go off to the final state, the new final state, and we are done with that. So this automaton really does have a language that's E star. You can go through the automaton for E 0 times by just going around it, or you can go through it once, twice, 3 times, as many times as you like. Now we're going to do the construction the other way. We'll start with a DFA and construct a regular expression defining the same language. The proof is inductive, and to make the induction work, we need to assume the states are named 1 through n. There's no harm in making this assumption, since the names of the states do not influence the language an automaton accepts. The induction is on the maximum number of a state that is allowed to be in the middle of a path, an idea that is explained on the next slide. We're going to talk about k-paths, which are paths that can go from any state to any state, but in the middle, that is excluding the endpoints, only states numbered k or less can be found. The inductive construction is on k, and it states that there is a regular expression whose language is the set of labels of all k-paths from state I to state j. We start with 0 paths as a basis, and by the time we get to n paths, there's no restriction on paths at all, so we have a regular expression describing the language of the automaton itself. Notice that an n path represents no restriction on paths at all, since there are no states whose names are higher than n. To get a regular expression for the language of the DFA, we take the union of the expressions for the n paths that describe how you get from the start state to each of the final states. For example, here's a little automaton. The 0 paths from state 2 to state 3 are the language of the regular expression 0. The reason is that we can only follow an arc from 2 to 3, and there's only one, the one that has label 0. That's the 0 is describes the only path that gets us from state 2 to 3 without going through any other state. The 1 paths from 2 to 3 can go through state 1, but not through 2 or 3. Thus, we can still follow the arc from 2 to 3 labeled 0, but we also can follow the arc labeled 1 from state 2 to state 1, that's this, and from there the arc labeled 1 from state 1 to state 3. Notice that once we get to state 1, we cannot go back to 2 in a 1 path, and if we go to 3, we're finished. The path must end. The 2 paths from state 2 to state 3 are more varied. The only thing we cannot do is pass through state 3. Thus, from state 2, we can go to state 1 and back to 2 0 or more times. The labels along each such path is 1 0, so 1 0 star describes the labels we traverse by following this path any number of times, including 0 times. After oscillating as many times as we wish and winding up in state 2, we can then follow the 0 arc to 3. That's that part of the regular expression. These paths from state 2 to state 3 are described by the regular expression 1 0 star 0. That's this whole part. An alternative plan is to oscillate between states 2 and 1, winding up in 1. The labels of all these paths are described by 1. That is, you can go to state 1 for the first time, and then you can go 0 1 0 1 as many times as you like, including 0 times. Finally, though, you have to follow the path from 1 to 3, the arc from 1 to 3, in fact. And so 1 followed by 1 followed by 0 1 star followed by another 1 describes all those paths that start in 2, go from 1 to 2 several times, wind up in 1, and then go to 3. The regular expression for the labels of all 2 paths from state 2 to state 3 is the union of these 2 expressions that we have just described. The three paths from state 2 to state 3 also have a regular expression, but it is sufficiently complicated that we're going to save that example until we have seen the complete construction. Okay, now here's the induction of how you go from a DFA to a regular expression. Okay, the basis is k equals 0. Notice that a zero path can have no intermediate states at all. Thus, the set of zero paths from a state I to state j can only consist of a single arc, plus, in the special case that I equals j, no arcs at all. We can construct a regular expression for this language. Connect with pluses each of the labels, and in addition, if I equals j, then add an epsilon. So, for example, here's state I, here's state j, and suppose it has an arc labeled A, B, and C, then its regular expression is A plus B plus C. And if there's also an arc, let's say, from I to I, in addition, let's say that there is a loop with labels D and E on the state I, then the regular expression for the paths from I to I would be D plus E plus epsilon. We now need to introduce some notation. Let Rij super k be the regular expression for the set of labels of the k paths from state I to state j. We've really seen the basis case k equals 0. That is, Rij super 0 is the sum of the labels on the arc from state I to state j. If there's no such arc, then use the empty set symbol as the regular expression, but we add epsilon if I equals j. Okay, here's our example DFA again. Okay. R12 super 0 equals 0, since that is the label of the arc from the state 1 to state 2. And, of course, state 1 is not equal to state 2. Now consider R11 super 0. There's no arc from state 1 to itself, so we start out with the empty set. However, since the beginning and end states are the same, we add epsilon. Okay, and incidentally, notice that there's an algebraic law. That is, the empty set union anything is that other thing. So whenever you see an empty set symbol plus something else, you can just get rid of the empty set and the plus and just take what's left there. Now we shall do the inductive step, where we assume we've written all the regular expressions with super k minus 1, and we need to write the expressions for the k paths. A k path either never goes through state k at all, or it does so one or more times. That lets us write the expression for Rij super k in terms of expressions for k minus 1 paths. The first term covers the case that the k path doesn't even go through the state k once. That is, every k minus 1 path is a k path. All other k paths get to state k at least once. Thus we start out with Rik super k minus 1, which generates us the labels of all the paths that get us from state I to state k for the first time. Then comes Rkk super k minus 1 all starred. It generates the labels of all paths that go from state k to state k 0 or more times, with those paths not passing through any state k or higher. Finally, we concatenate with the language of the expression Rkj super k minus 1. That generates the labels of all paths from state k to state j that do not pass through state k or higher. Okay. Here's a picture of what a k path looks like with the vertical axis representing the state number. We've shown I and j above k, although they could be at any height. That is, for example, I could be down here, so could j, could be down there, or they could be higher. Doesn't matter. Okay. So one possibility is that the k path never goes through state k, or it could go through state k for the first time, but only through lower states. And from K to K, you could go, again, through lower states 0 or more times. And finally, you go from K to J through lower number of states, states numbered lower than K. And that represents all the paths that go from I to J through K and lower numbered states. Finally, as we have hinted, the regular expression with the same language as the given DFA is formed by taking the union over all final states J of Rij super n, where I is the start state. Okay. So here are our example DFA again. Now we have to install a start state and some final states. So let's assume that state 2 is the start state and 3 is the only final state. So the regular expression that we want is just R23 super 3. Okay, here's the expression for R23 super 3 in terms of the super 2 expressions. This expression is special because state 3 appears in two places as both K and J, and as a result we can simplify it as shown to R23 super 2 concatenated with R33 super 2 star. The reason is that if E is any regular expression such as R33 super 2, then E star E is the concatenation of one or more E's. Okay. Now we have another expression, R23 super 2, that you can think of as itself concatenated with none of the E's. Remember, E is actually R33 super 2. So this is R23 super 2 concatenated with no E's. This is R323 super 2 concatenated with E star E, that's one or more E's. So together you have R23 super 2 concatenated with 0 or more E's. And that's what this expression is saying. Again, remember E is R33 super 2. Okay, so we figured out what R23 super 2 is. We did that earlier, so let's just use it here. Okay. And here's an expression for R33 super 2. I won't give the details, but remember that this expression has to represent paths from 3 to 3 that never go through 3, so it could only jump from 1 to 2 and back again until it returns to 3. And here is the simplified expression composed of R23 super 2 and R33 super 2, that last being starred. So what you have at the end is a regular expression whose language is the same as the regular expression of this automaton in the corner. Each of the three types of automata, the DFA, the NFA, and the epsilon NFA that we discussed, and regular expressions as well, define exactly the same set of languages, the regular languages. That is, if you remember, we started with the DFA, and we showed that any NFA could be converted to a DFA, that's the subset construction. We then showed that any epsilon NFA could be converted to an ordinary NFA, that was sort of the closure construction. And earlier in this lecture, we showed that any regular expression can be converted to an epsilon NFA. And now we just showed that every DFA can be converted to a regular expression. That says any language defined by any one of these four notations is defined by all the others. Okay, we're going to finish up with a little discussion of the algebraic laws for regular expressions. We have several times argued that two different regular expressions represent the same language, and therefore one can be substituted for the other. These are examples of the sort of algebraic laws that we find in the algebra of regular expressions, of arithmetic, Boolean algebra, and other algebras. The laws for regular expressions are not too different from those for arithmetic, but we have to be very careful to observe the differences. First, plus and concatenation behave almost like plus and times for arithmetic. The plus operator, which remember is set union, is associative and commutative just like addition. Remember also that the commutative law says that x plus y equals y plus x. That is, the order of the arguments doesn't matter. Okay. The associative law says that you can group the operator in any order, or formally x plus y grouped plus z equals x plus the grouping of y plus z. That is, you can apply plus to the first two arguments first or apply it to the last two arguments first. It doesn't matter. The result is the same. Concatenation, like multiplication, is associative. Moreover, concatenation distributes over union just like multiplication distributes over addition. That is, x concatenated with y plus z equals xy plus xz. That is, x, y plus z equals xy plus xz. That's the distributive law. Okay. The big difference between regular expressions and arithmetic is that concatenation is not commutative, although multiplication obviously is. That is, the regular expressions AB and BA don't denote the same languages. That is, the first, AB, just denotes the language that contains the string AB, while the second, BA, denotes the language that contains only the string BA. Okay. Arithmetic also has certain constants that serve as identities for addition and multiplication. Obviously, 0 is the identity for addition, and that adding 0 to any number gives you that number back. Likewise, 1 is the identity for multiplication, because multiplying any number by 1 gives you that number. Finally, 0 is also the annihilator for multiplication, because multiplying any number by 0 gives you 0. Union and concatenation have analogous identities. As we shall see, the identity for union is the annihilator for concatenation, just like the identity for addition is the annihilator for multiplication. Now, the identity for union, as we actually have mentioned, is the empty set. Obviously, taking the union of the empty set with any set yields that set. The language containing only the empty string is the identity for concatenation. Concatenating any string S with the empty string yields S, so concatenating the language represented by the regular expression epsilon with any other language, say the language represented by regular expression R, will result in the same language, the one represented by R. Finally, the empty set is the annihilator for concatenation. That is, if we take any language, say the language represented by regular expression R, and concatenate it with the empty language, we get the empty language. Why? The result of the concatenation requires that we take strings from both languages and concatenate them in all possible ways. But you can't find any strings in the empty language to use in the concatenation of strings.